Okay. Yeah, thanks for putting this workshop together and inviting me. I'm going to tell you today about mesogenesis. Okay, so we had a kind of nice introduction to baryogenesis yesterday, so I don't need to remind you that we would like to understand, or we'd like a dynamical mechanism to generate the primordial asymmetry, which is measured from BBN and C and B. And this mechanism, has to happen sometime between inflation and BBN, right? So I'll remind you that there's a lot of kind of traditional mechanisms, going back to when Sakharov first proposed the conditions required to generate a baryon asymmetry, starting with, like, for instance, gut baryogenesis, electroweak baryogenesis, which uses the electroweak phase transition. But these all kind of happen at high scales, I would call. And I would argue that they're traditionally hard to test, or in the case of electroweak baryogenesis, pretty constrained by EDMs. So what I'm going to tell you about today is a mechanism for baryogenesis that actually occurs very, very late. In particular, it occurs sometime between the QCD phase transition and BBN. So it's order and MEV scales when this happens. And this is a mechanism for generating both the baryon asymmetry as well as the dark matter. And it turns out that because this happens so late, it's actually directly controlled by experimental observables, and there's a lot of signals, and it's being tested right now. There's some results already from some experiments. So this is, I think, very exciting. It's also theoretically appealing if you need baryogenesis to happen late, like, for instance, for various solutions to the hierarchy problem. So with that in mind, here's kind of a global overview of how this particular mechanism will satisfy the three Sakharov conditions, okay? So you need to be out of equilibrium, of course. I'm going to generically do this by assuming there's some scalar field. I'll kind of refer to it as the inflaton. It's not necessarily related to inflation, but I'm going to kind of table that conversation. But the point is this field is going to decay pretty late. So at MEV scales, it's going to decay into quarks, and they're going to hadronize to form standard model mesons. So kind of the tooth fairy in all of this is the scalar field that generates mesons at late times. CP violation is going to come from standard model Meson systems. Okay, I already have CP violation in standard model processes, and I'm going to get it from these processes directly. It's a very kind of novel way of getting the CP asymmetry. And finally, you need baryon number violation, quote unquote. I will never actually break baryon number in these setups. Instead, I'm going to hide it in the dark sector. So I'm going to have dark sector states charged under baryon number, or sometimes lepton number, and I'm going to generate kind of an equal and opposite asymmetry between the dark and the visible sector. So I'm never actually breaking baryon number. Okay, so kind of today, there's many different flavors, if you will, of this mechanism. So, okay, there's a lot going on in this table right now. I'm going to return to the details of this table later. The point is right now is there's kind of different scenarios for doing this. They involve CP violation from different flavors of mesons in the standard model. They all have various different implications for the dark sector, and they all have various different observables, which are testable to various degrees. This is kind of organized from, like, the most testable, which is really testable in the next 5 years, to kind of something that you need maybe a future circular collider for. And then here's some references. I probably will not go through and show you more references in this talk. But kind of the goal of the talk is to give you an overview of all this work today. So I don't want to make it super technical. So it's going to be an overview, and hopefully I'll just give you kind of a flavor, unintended, of these mechanisms. Okay, so with that, let's begin. I'll begin by reminding you that neutral B-Meson systems undergo particle-antiparticle oscillations, okay? For instance, in the standard model, they come from a diagram like this, these kind of box diagrams. These diagrams, even in the standard model, right, there's CKM phases in it, so these processes, they violate CP, right? And the way to measure this in experiments is to consider processes like this, where you have a B-Meson, this Q can be an S or a D, and it oscillates into an anti-Meson and decays into some final state. And the observable that the experimentalist measurement is simply the difference between these decays, the decay and the conjugate, over the sum. Okay, so this is referred to as the charge asymmetry or the semi-Leptonic asymmetry. And for the purpose of this talk, I'm using these two observables interchangeably. Feel free to also stop and ask me for questions. Okay, so here is kind of a summary of the CP violation or the charge asymmetry in the B sub S system versus, the B sub D system versus the B sub S system. These are the standard model values, and these bands are the experimental uncertainties. And this this D0 result, I'm told, is slightly contended, and maybe don't take it too seriously. But the point is, the standard model value is actually quite large. And there's a lot of room for new physics in this observable as well, right? These are big error bars. Okay, these are numbers, order 10 to the, even in the standard model, it's order 10 to the minus 5, 10 to the minus 6, which is a huge number if I think about it, but I want to explain a number that's 10 to the minus 11. Okay, so how does the mechanism actually work? So let's go through the Sakharov conditions in a little bit more detail. Out of equilibrium decay, I have some field, I'll call it the inflaton for now. It doesn't need to be the inflaton. It's actually quite hard to make it be kind of a vanilla inflaton, but it could be like a Saxion field. It could be kind of a reheaton in a multi-inflaton model. But it doesn't matter so much for the purpose of this talk because I'm just going to assume that it exists and it decays into quarks, into QQ bar. At MEB scales. Okay, so sometime before BBN, but after the QCD phase transition. I'm going to, for the purposes of this mechanism, I'm going to choose the flavor couplings of this guy such that it hadronizes into an equal number of neutral B sub S and B sub D mesons, and then they undergo CP violating oscillations. Okay, so out of equilibrium decay, CP violating oscillations, directly related to an experimental observable. Any questions?
Yeah, can you please explain why the boundary on the maximum mass and temperature idea?
Yeah, so I don't want this to happen during BBN, okay, because that would be bad, right? And then I want it to happen after the QC phase transition because I want these guys to immediately hadronize. Okay, I don't want quarks to be floating around. I want to create mesons. That makes sense.
But would it be bad if it's a bit larger? It's impossible.
I mean, for this mechanism, I want it to happen. I want the things to hadronize. You could consider kind of a hybrid scenario, but what that's going to do is generate washout effects. And actually, well, this temperature should actually be lower to avoid washout effects. But in the simplest scenario, like this is the simplest zeroth order thing to consider. But we do have a project right now, which is seeing how far up we can push this temperature.
Which washout effect?
So for instance, if you have, so if you have scatterings around, I'll talk a little bit more about it later. It'll become clear. But yeah, scatterings, for instance, I'll explain the mechanism first before talking about the washout. Okay, so now baryon number. I need a way to change baryon number. You could introduce baryon number violating couplings, but those are going to be constrained. There's going to be constrained from bounds on NN bar oscillations, for instance. And it's going to be a lot more constrained. So instead, I'm going to hide the baryon number in the dark sector itself. Okay. So how I'm going to do that? I'm going to assume that there's a dark sector state. The cartoon picture of that is: imagine I introduce a dark fermion, and it carries anti-baryon number -1. And I'm going to imagine a model where the B meson, after having undergone late time production and oscillations, then decays into this dark baryon and into a standard model baryon. Okay, so this seemingly violates baryon number in the visible sector, but really it's just hiding it. And even before writing down a model, obviously, I need the kinematics to work out for this to be possible. And I also want to stabilize matter, right? I want to forbid proton or neutron decay. So the easiest way to do that, or really the only feasible way to do that, is to just require this new state to be heavier than the proton. Okay, so I have a mass window of 1 to 4 GeV for the mass of this particle. Okay, this new state. That's a very specific window. And hopefully it's clear that the end result of this whole scenario is the production. These are yield variables, so number density over co-moving entropy. So the baryon asymmetry in the visible sector is going to be equal and opposite the asymmetry generated in these new dark fermions. Okay, does that make sense? Okay, so how do I actually do it? Let me write down a model. So I have again, I have my dark baryon. It needs to be GeV scale for kinematics and to forbid proton decay, charging it under baryon number. I also need a mediator. I needed to talk somehow to the standard model. So I'm going to imagine that there's some new colored scalar particle. It's at the TeV scale to evade collider bounds. This is basically a squark, if you will, in a supersymmetric model. In fact, I don't have the number here, but we have a paper where we embed this very nicely in a supersymmetric theory. So you can think of this guy as a squark, and you can apply all the kind of collider LHC constraints on squark searches. So yes, it has to be TeV, and then you can write down the following Lagrangian, right? So you can couple this mediator to two quarks, or you can couple the mediator to a quark and this field. Then I integrate out the mediator. I'm at MEV scales, and I'm dealing with the following kinds of operators. Okay, so it's 3 quarks and this new dark fermion, and this is Baryon number conserving. Okay. So this operator will then allow in this particular case, the B anti-quark within the B meson to decay into 2 quarks and the dark guy, and this hadronizes to form, for instance, a lambda baryon. Okay. So this is the kind of decays that I'm considering. And yeah, any questions? Okay. So what about the dark matter? Okay, so I told you that this new guy has to be GeV scale to forbid proton decay, but then, well, it could just decay back into a proton. Okay, and then, well, it's obviously not the dark matter, and of course I've washed out the asymmetry because I've just decayed back into the standard model. So I need another ingredient, and what I need to do is to actually introduce 2 more states in the dark sector, and also a Z2, for instance, to stabilize them. So I'm going to introduce a dark fermion and a dark scalar with the same baryon charge as this guy. So it has to be, again, GeV scale. And I have a Z2 so that I can write down, for instance, a Yukawa coupling between these 3 guys. These two, this one is going to be even, and these guys are going to be odd under the Z2. And then I can stabilize the dark sector this way. Okay, the lightest of these 2 or some combination of them will be the dark matter. For the purposes of this talk, what actually is the dark matter is less interesting because it's less directly testable. So the thing to keep in the back of your mind is, okay, some combination of these particles will always generate the dark matter abundance. And then this all happens pretty quickly. So the asymmetry from here is just transferred to the asymmetry from here, and I get kind of the same result for the visible sector asymmetry.
But sorry,
yeah.
These state are produced by the decay of the psi, no? So the dark matter. Like,
yes.
So they're gonna be they are produced relativistic. So
I mean, it's not necessarily. It's all low scale.
No, I mean.
But okay, what are you?
They can't be relative in the sense that they are produced from decay. So
okay, yeah,
at the
sure.
beginning they're relativistic.
Okay.
So I was wondering, since you have very light states in general, if like one dark matter constraints, they're not relevant here.
No, because they're still going to be. I mean, this is still like GeV scale, so I don't. Yeah, I mean, maybe there's a scenario where you can worry a little bit about.
I'm sorry,
this.
I thought that these. So okay. So psi is GeV.
It's GeV, yeah. This guy can be light. So there is some. Yeah. So you're right that maybe there's some parameter space where we're up against the warm dark matter. But also I'm not going to show you a dark sector model. But yes, that's something. No. Did that answer the question?
Yeah, no, I was just trying to understand. Sorry, this psi.
So it's GeV scale decaying into GeV scale.
Yeah. Okay. I see. No. Yeah, there is space. I understand. Yeah. Okay.
Yeah. It would be interesting actually to write down kind of a detailed dark sector model for this. That's kind of a back burner project. Any other questions? Okay, so if not, I don't want to make this talk too technical, but just to show you that I'm not completely making this up, here's kind of the Boltzmann equations that you can, that you would write down to actually, solve the evolution of the number densities. A couple takeaway points, right? You have to track the decay of this inflaton. You have to track the radiation. And then you have the kind of the symmetric component of this dark scalar. and the antisymmetric component, which gives you the baryon asymmetry. Now I'm going to assume this all happens very, very quickly, which is we checked is a pretty reasonable assumption at this late times, and so this is why I'm not showing you kind of all the other particles, but you can certainly check that this is a good approximation. A couple takeaway points. There's this F function here. What this does is it tracks the decoherence of the oscillations. Okay, so I need to be careful that these oscillations are always going to there's nothing around to measure the oscillations and decohere them. The only thing kind of that can do that at these late times is electron scatterings off the charge radius of the B-mesons. So that's something that you have to track, and it turns out to kind of require that the temperature is sufficiently low so that the oscillations are coherent. And then the other thing that's going on here is I've introduced this sigma B, which is a dark sector scattering. And the reason I need this is because this mechanism generically overproduces the dark matter. So I have some additional dark sector scatterings, which kind of do a freeze out in the dark sector, which also you would expect because you have, for instance, co-annihilations between these dark sector states. Okay, that was a lot of words. Let me show you an example benchmark point. So what's going on here? So this blue line is just the decay of the scalar, kind of boosted by a factor of -4. The red and the black are the dark sector particles, so the symmetric component of the scalar and then the fermion. And as you can see, they're basically undergoing a dark sector freeze out. Okay, for this cross section that I've chosen to be like an order of magnitude greater than like a typical limb cross section. And then the asymmetry is this brown line here. And what happens here is, so at around 20 MeV, that's when coherent oscillations of the B sub S field turn on. So when that happens is related to like what the temperature is relative to the oscillation parameters. And then it increases the asymmetry because I've chosen a positive value for the semi-Leptonic asymmetry in the B sub S system for this benchmark. And then at 10 MeV, coherent oscillations in the B sub D system turn on. And for this benchmark, I've chosen a negative value, so it actually slightly decreases the asymmetry. But this benchmark point has been chosen such that it reproduces the right asymmetry in the end. So the takeaway from this is that I need kind of a net positive charge asymmetry for this mechanism to work, okay? Because I need to, like, the sign actually matters. And kind of because I have a lot of free parameters in the dark sector, I have the masses and kind of the couplings between these particles. I've kind of chosen it such that I get the right dark matter abundance for this particular case. Okay, any questions? Okay, so hopefully I've now given you kind of a picture of this mechanism. I have very late time production of mesons. They undergo CP violating oscillations, the B sub S and the B sub D system. They decay into a standard model baryon and dark sector particles. And if you run the Boltzmann equations and study the parameter space, what you find is that the asymmetry, right, is it's directly related to the branching fraction of this new decay. So this is the B meson into a standard model baryon and missing energy. And the charge asymmetry in these oscillations, plus this alpha Q parameterizes the parameters of this guy, so the mass and the temperature, but it's actually a pretty weak dependence. So really, in order to get this, in order to produce baryon asymmetry with this mechanism, I have an experimental prediction, which is that the product of the semi-Leptonic or the charge asymmetry times this branching fraction is going to be greater than 10 to the -6. Okay, so this is a prediction of getting successful B-Mesogenesis. Okay.
What was the sorry,
shit. Sorry, what was that?
What was the branching function of the B to psi B and then what is
so it's sorry, this is like an additional meson, like if you radiate off a pion. That's okay, so my slide's not showing up. Let's see, is that okay? So let me describe what's supposed to be on the slide. Basically, there's a lot of signals you can look for, right? So there's the semi-Leptonic asymmetry, there's this new branching fraction, but there's also going to be additional decays that this model induces. For instance, you can have B-flavored baryons decaying into mesons. Okay, so that's kind of an indirect signal. On top of that, you have your flavor observables, and then you have, because you need this this new TV scalar mediator, you have a lot of collider signals, okay, and you have constraints on the mass and the couplings of the scalar mediator. So that's kind of that's what goes in there. There's a bunch of indirect signals. So let me kind of walk you through the current state of testability of this mechanism. So here I have the semi-Leptonic asymmetry, again, in the B sub S system and the B sub D system. So this yellow box is the current world averages on these measurements, and experiments like Bell and LHCb are planning to improve these measurements anyways. I don't have to convince them to do it. This red region is where the branching fraction is large enough to achieve baryogenesis using this mechanism. Okay, so these are different bands with different uncertainties going into it. This black box is the standard model values. And this gray line is an old search by Aleph that we recasted the bounds on these branching fractions. So basically the allowed regions of parameter space now exist in this box, which I'm outlining here, okay? So unfortunately, that means that the standard model CT violation is not actually enough to generate the observed baryon asymmetry in this mechanism. But again, that's okay because I have a lot of room for new physics. And indeed, if I have like a supersymmetric model, and we have a paper on this, there's going to be additional CP violating phases and squarks running around the loop in these box diagrams that contribute to the asymmetry, and you can get enough CP violation in a model like that. Okay. All right. So now the decay. So I gave you one example before where I had the decay into lambda baryon, but of course there's kind of all these different flavorful variations of this model. And indeed, I can do successful baryogenesis from kind of 4 different operators that correspond to different kind of flavorful couplings. And each of these operators correspond to different decay modes of not just the B sub D and the B sub S, but also charged V mesons and lambda baryons, as I was saying before, right? It's the same couplings, and they go to different final states, right? So directly related to the baryon asymmetry, kind of an indirect signal, and then additional indirect signals, okay? So this is the branching fraction that feeds into the baryon asymmetry. And at the time when we first proposed this mechanism, this first mechanism we proposed back in 2018, the limits on this branching fractions were like order 1%. We improved that a little with the Aleph search, but this was just something that, like, it was almost surprising to us, but yeah, it's a seemingly baryon number violating decay, and people just haven't searched for it until the Bell collaboration, motivated by our model, did a search for this particular channel. So this was a result that they released, I guess, a year ago now, of the B sub D decaying into a lambda and missing energy. So this is their limit. It's order 10 to the minus 5, so that's not enough for this. So they did not discover our mechanism because it's 10 to the minus 5. It basically says that this operator is looking disfavored for generating all of the baryon asymmetry. Okay, but then that's just one channel. There's all these different operators, and indeed, I think they're planning to. Well, they want to look for other decay modes, and LHCb has a proposed search that can look for all of the different final states, as well as lambda B baryons. Okay, so I want to kind of pause a little bit, and or I want to, yeah. So the branching fraction that I wrote down before is an inclusive rate. Okay, so it's all of those operators could, all of these operators could contribute to that. But of course, the experiments are going to look for certain channels. So it's actually pretty important for us to go ahead and calculate what the actual branching fractions are for these decays. So this is just to highlight some ongoing work that hopefully this paper will be out in the next month or two with a grad student at Padova, where we're actually calculating these branching fractions using the machinery of like home QZD sum rules. There was also a paper by the experts that came out like pretty recently, but okay, they did one of these modes and we're agreeing with them. But yeah, so the point is we'll be able to tell experimentalists like, okay, really this is the prediction within this model given LHC constraints and things like that. Okay, so here's kind of the overview of the current state of this particular, yeah.
In your previous plot, what are the constraints on the Breaching ratio?
So right now I have simply set the Wilson coefficient, if you will, to be this value, which is the most it can be given collider constraints. That, yeah, and we have a whole paper on that I can reference you to. Okay, so this is kind of the money plot for this particular flavor of mesogenesis. So basically, this is the parameter space that can successfully generate the Baryon asymmetry. And this is a standard model. Of course, it's excluded. But the point is that if these experiments, improve their measurements on the charge asymmetry, so these arrows are kind of the 2025 projection limits for how well they think they can make this measurement. And then, of course, if Bell and LHCb measure the branching fraction, this mechanism can be tested in the next 5 years. Okay, so we'll either discover it or we'll kill it, but that's pretty exciting. In addition, there's some indirect signals for this mechanism. So for instance, we looked at, the same mediator will generate the decays of, in this case, hyperons, right? For instance, into mesons and missing energy or completely invisible. And you can actually calculate the form factors for that using chiral effective theory. And so this is some kind of results we have for that. So this is nice because experiments like BEST2, which for instance measured this decay, lambda completely invisible decay of a lambda baryon, actually place kind of indirect constraints on this mechanism. And if you have that, then you can start asking about, okay, what are the flavor observables and what kind of flavor structure do these models have? And I'm not going to go into the details of that. Another indirect signal, which is something also that's kind of in preparation, is this model will induce nucleon decay. Okay, so a dark sector state will come in, it'll scatter off a proton or a neutron, and it'll produce a very energetic light meson and missing energy. So this is something that Dune and also Super K and Hyper K can look for. This is a monoenergetic signal. It's unconstrained by their current searches because it's just different kinematics. And the cross section, this is kind of what this plot is showing, is large enough for these experiments to have sensitivity to them. So this is a search that we're proposing. Okay, any questions? Okay, so I think you should be asking me, why was I so obsessed with neutral B mesons? There's so many standard model mesons and there's lots of CP violation in them. So did I just spend I don't know, half an hour telling you about B mesons?
Because they're heavier, no?
Exactly, because they're heavier, thank you. So indeed, it's a kinematic constraint, right? I wanted to create proton decay, and this was kind of the only system I could do it with, right? So, okay. But if I ask the question, okay, say in the next 5 years we don't see this mechanism, does that mean that these sorts of things could just are completely excluded? So there's actually different things you can do, and the trick is to first generate a leptonic symmetry, because if you decay into leptons, you're not bounded by stability of matter, and these states can be light. So let me tell you about a different flavor of this mechanism. I guess I have 15 minutes. Is that right? Okay. Yeah. So maybe I'll go. Give you an overview of these other flavors. So in this case, I want to use the CP violation in the charge system. Okay, so charged D mesons have CP violation in their decay. So this is a direct CP violation, and the asymmetry is just the difference between the decay of the charged meson into its conjugate. So in some sense, it's simpler because I don't have the oscillations. And if I pull up the PDG and I just look up at limits, so these are not the standard model values. I don't know how to calculate these values in the standard model, but these are just the current limits on these the asymmetry in these decays, and they're quite large, right? Again, I'm trying to explain an order 10 to the minus 11 number, and I have very large asymmetry. So let's try to leverage the CP violation in this system to do baryogenesis. So the idea is very, very similar to the one I just told you. In this case, this inflaton reheaton type field will decay into quarks, but in this case, they'll hadronize into D mesons. So I'm just choosing the flavor couplings of this guy such that I'm just considering this. It's going to happen before BBN and after the QCD phase transition. I'm actually going to choose 20 MeV here again to evade washout effects because I want these decays to be the dominant process. I don't want scattering between the D mesons and other particles that may be around or pions that get produced. So yeah, this goes back to someone's question that I'm just making a temperature low enough so that I don't need to worry about washout. Then I'm going to have these produced D mesons decay into some final state and introduce a CP violation. Let's just consider the pions because that's the table I just showed you. And then what I've done here, right, is generate I have out of equilibrium decay and CP violation. Okay. Again, I can't have them decay directly into baryons, so I'm going to have them decay into leptons. And I'm going to first generate a lepton asymmetry. One way to do that is through a Portal operator that looks like this. Can come from like a left-right symmetric model with a vector mediator, for instance. These kind of operators get written down a lot in the context of like sterile neutrino models. And this operator will allow the charged pion to decay into a dark lepton and a standard model lepton. So this looks a lot like, yeah, like a sterile neutrino model, right? Except that I'm not constrained by the oscillation parameters.
So
yeah,
I don't understand something basic. So this phi that decays into Q2 bar.
Yeah.
So this is the guy that gives you essentially the abundance of B's of Meson, because otherwise it will not be there, right?
Yeah.
So
I need this guy to dominate the energy density at late times. So I have a late matter dominated
here.
Yeah.
I see.
Yeah.
I see.
Okay.
Okay, no, sorry.
Okay, good. Thank you. I should have said that.
Yeah.
Any other questions? Okay, so this is the cartoon version of how I generate, in this case, a lepton asymmetry, right? So out of equilibrium decay, CP violation, and then decay of this light meson. And I can write down the Boltzmann equations and solve them, and which I'm not going to do in the last 15 minutes. But the point is now this lepton asymmetry in the dark sector, which is going to be equal to a lepton asymmetry generated in the visible sector, is going to be directly controlled by, again, kind of the observables in each stage of this process. So in this case, it's the CP violation and the branching fraction in this process, and then this branching fraction of pions into leptons and anomalous missing energy. Okay, plus some weak dependence on the inflaton parameters. Okay, so this is the result of solving the Boltzmann equation. So again, this is the observables in the B sub D system. This n is some number of pions, and then this is the pion decay. And this region that's green, but maybe hard to see on the slide, is where I produce as much lepton asymmetry or more relative to the baryon asymmetry that I would need, okay? Because the idea is like I'm going to somehow transfer this lepton asymmetry into baryon asymmetry, and there might be some inefficiency there. So this is the parameter space where this model works. What this dotted line here is kind of the central value of the current exclusions from all those processes I showed you in a couple slides ago for the limits on the kind of the product of these parameters in the B sub D system, just for measurements. Okay, so this is not a theoretical prediction. And then this is where they're just too big to agree with measurements. This dotted line here is actually a limit from a peak search from the Psi experiment, which looked at pions decaying into leptons, into muons and anomalous missing energy. And the point is you can take these peak searches, which are, they're searches for sterile neutrinos, but they're very model independent, and you can recast them onto. So this is like the oscillation parameters for the sterile neutrinos. You can recast it into a limit on this branching fraction. But the main thing to note here is that these peak searches very much depend on kind of the mass of the missing energy. So in this case, the dark lepton. So take it with a grain of salt. There's kind of always parameter space to evade these limits. Nevertheless, people on these experiments, this is kind of another model that they can now probe. So that's kind of nice. Okay, so any questions? We'll pause. Okay, so right, great. I generated a lepton asymmetry, but I haven't actually done anything because I want to generate a baryon asymmetry. I can't use electroweak scalars, right? Because I'm at MeV scales. Turns out I don't need them. I'm going to do something crazy, which is put a couple more states in the dark sector, because why not? I have a rich dark sector, and I could spend a completely different talk motivating you on why rich dark sectors are worth thinking about, but I won't do that.
Sorry, one second. These now you have also dark leptons, but you have only portal. So you're not considering a portal with like standard model leptons. So they only talk to standard model baryons, or like how it?
So this lepton state.
Yeah, LD. Why?
No, so this talks to the standard model. So this is, this is like, for instance, this portal. Okay.
Yeah, but I would also have like the same with the L bar L, no? Or not?
L bar.
Like why can't just write purely leptonic operators?
Because I want the meson to decay.
No, but I mean.
Yeah. Yeah. So certainly you could. Yeah, certainly you could. Absolutely. Yeah. I'm not
saying at the zero level.
Yeah.
There are, we know much more about muon decays than about pion decays.
Yeah, no, so you're absolutely right. If I was going to write down like a full toy model for this dark sector mechanism, then I would have all these indirect signals from the decays of leptons and other constraints. So yeah, no, you're absolutely right. I just haven't found that yet.
Okay.
Yeah. Again, those kind of things are on the back burner. Yeah, so, but yeah, before that, I want to convince you that it's not crazy to generate the Baryon asymmetry this way. So that's the dark state I just introduced. I have two more states. I can kind of have different charge assignments to get this to work. But in this case, I'm going to have a dark sector scattering that conserves B and L number. And I'm going to have this dark lepton come scatter off another dark lepton and turn into a dark baryon in a standard model baryon. And I need some additional portal couplings. I can actually use exactly the same model that I wrote down before. I just now envision this to be a mass mixing instead of a decay. But what this cartoon is hopefully convincing you of is that, yeah, schematically, what I'm doing here is I'm transferring the lepton asymmetry into a baryon asymmetry. Okay, so again, not writing down the Boltzmann equations, but here's one benchmark where it can work. Because the main thing you should be complaining about is saying, okay, I have this dark sector scattering in these models, which is kind of sigma v in this Boltzmann equation that's tracking the baryon asymmetry with respect to the lepton asymmetry, and this sigma v is going to be constrained, right, from the model I just wrote down, right, from collider searches and things like that. So the question is can this scattering be large enough to efficiently transfer the asymmetry while being consistent with any experimental searches on it? And so in this benchmark, it turns out that it is. Again, this blue line is the inflaton decaying. This green line is the dark lepton asymmetry. This kind of funny peak is because of this matter-dominated era. I'm not going to go into too many details. And this red line is the baryon asymmetry, which is basically freezing into its expected value. Okay, so this is a possible way to do it. So this is kind of the summary of this scenario. You first generate a lepton asymmetry, and then you freeze in a baryon asymmetry. Okay. Again, kind of all the different processes here have observables, which you can measure. But because you're first producing the lepton asymmetry, it is it is less testable than the first mechanism I told you about, than the neutral B-Mesogenesis. But then nevertheless, this is, and yeah, like you were saying, if you write down an actual model here, you will have a lot of model-dependent signatures, and you could really propose searches for this. Okay, so of course you could do the same thing with the B+ system. So exactly the same thing. I'm just imagining that I produce B+, they decay into some like mesons, not even just pions, they could be kaons or even D-charged D mesons, and you have the same scenario as before. I have this parameter space with all the different kind of lines for the different final states. And the reason why this particular scenario might be interesting is because these decays are like supposed to have a lot of CP violation with them, just within the standard model. I don't know what those values are because they haven't really been calculated, but this is kind of one way that maybe could do baryogenesis with just the standard model CP violation, up to the caveat where these things need to be calculated. And finally, just very quickly, you could kind of come back full circle and say, okay, like what's the kind of the simplest version of this setup? And I would argue that that's actually, if you first decay into like a heavier B meson, so B sub C meson, which is 6 GeV, then it can decay directly into a charged B meson and then directly into the dark sector. Okay, so you don't need to produce Lepton asymmetry, you don't need oscillations, you simply have this pattern. And again, the observables of this decay and this branching, this decay and this decay will feed into the asymmetry. This arises through exactly the same model that I wrote down before. So they have a colored mediator. So is that my timer? No. So what's kind of cute about this, even though it's I mean, B sub C physics there's a lot of proposals for it at future circular colliders, and LHCb has a proposed program for B sub C physics. But kind of the neat thing is that kind of what was the direct signal for neutral B-Mesogenesis is now the indirect signal for this mechanism, and vice versa. Okay, so now this branching fraction is going to be the one that kind of feeds directly into the asymmetry. So it's kind of a complementary region of parameter space that experimentalists can go look for. Okay, so that's just the summary of this mechanism. The Baryon asymmetry, again, related to the CP violation and the branching fraction of these two decays. And then here's my parameter space, right? So very much unconstrained along this axis. This is the B sub C decay parameters. And along the this axis, which is the B plus decay, I've put in the Aleph constraints. And actually, this is that's the lambda. This is the LHCb constraint, the new one. No, sorry, this is an old plot. I apologize. LHCb constraint is down here. But yeah, so this is the allowed region where I produce the Baryon asymmetry this way. Up here, again, this comes back to the washout effects. This is where I produce more Baryon asymmetry than I actually need. So in this region, I'm actually cranking up the temperature such that I'm a little bit above the temperature where scatterings become important. And I actually have like some washout effects here. So that's something that we're currently running the Boltzmann equations for. And this is just the asymmetry feeding into that. Okay, so yeah, hopefully now this plot or this table is a little bit more meaningful to you. I've kind of given you an overview of 4 different mechanisms, starting with leveraging the CP violation in neutral B-Meson oscillations. This is very, very testable, maybe even discoverable in the next 5 years. Then I've kind of cast the challenge of how to do this with lighter mesons, the B sub D system and D plus system and B plus system, and all the different kind of observables that go into this. And then finally, I've given you kind of an example of the simplest scenario. Okay. So any questions about that?
Can you just summarize also in which case the CP validation of the standard model is enough?
So it's definitely not enough here. We have now recast the search. It's not looking like it would be enough here just because the charm system, kind of the standard Loris, doesn't have that much CP violation, but it would really be this mechanism where it might be enough. But I don't know because we would need to calculate these branching or the CP violation. And that's something that, yeah, that hasn't been done yet. Okay, so in the last 2 minutes, I wanted to actually zoom out. Now, of course, I think that I want this mechanism to be the one that describes nature, but also I feel like there's a lot of work right now on kind of very new ideas for baryogenesis. For instance, kind of all of these and many, many more. And all of these new ideas, a lot of them are also testable as well. So I just wanted to advertise our program in 2023 at Minds. So if you're interested in kind of new ideas for baryogenesis, or we'll probably also open up to general BSM stuff as well, you can come hang out with me in Minds in 2023. But with that, I will end.
Yeah, thank you. Are there any more questions?
So there are some BSM models that specifically want low reheat temperature, like if I remember, like large extra dimensions. Would this fit in naturally into those? Would this be a solution for the baryogenesis problem?
Yeah. So this was kind of my point very early on was that any mechanism you have that needs low reheating, you could.
This would do it.
This would do it. Yeah, I mean, you could ask the question of like, what other signals your extra dimension model proposes,
Right,
and how
right.
completely
Yeah.
disgusting it would be to have all this other new physics going on. But yeah, this is, as far as I know, one of the very few mechanisms where you can produce the Baryon asymmetry or the Lepton asymmetry at late times.
Mm-hmm.
Kind of related to a question that got asked yesterday. Like, we also played around like with this mechanism because we produced Lepton asymmetry. We're like, oh, is it enough to, like, for instance, solve the H-null tension? Turns out it's not. You just don't produce enough Lepton asymmetry. But yeah, there are scenarios where, you know, this could do other things.
But you said that you because another example besides the extra dimension would be supersymmetric models where, like, you know, there is a lot of overabundance, no? So you want to not rate very high, like
Sure, yeah.
So you said that you embedded this in RPV essentially, no?
Yep. Sorry.
It is just.
I will show you the charge assignments for that. I think I have it somewhere. Yeah. So this would be the kind of the supersymmetric embedding.
So there was this.
And sorry, wait a second.
You get only one
This guy. So the particles are heavy enough.
Yes.
So these operators are. So the cutoff is high enough.
Yeah. So in this paper, which I'm sorry, I don't have the archive number for, but yeah, we actually checked that given this embedding, I mean, this was also, we needed direct Gauge-Genos, you know, also for bounds on the, in this case, the direct Gauge-Geno for us, we identified with the side particle, for instance. Yeah, I mean, given all the different collider constraints, this mechanism will work.
I see.
Yeah.
There used to be, I have some vague memory of a paper by Savas and I think Lawrence also, right?
Probably.
No, low scale Baryon-Genesis.
Yeah.
Operator, right?
Yeah, I know the
Is
paper.
still alive?
I know the paper you're thinking of, but I don't remember the details. I'd have to look at it. Yeah.
Thanks, man.
Yeah. I'm sure that maybe I'm channeling my advisor here, but I'm sure that Lawrence probably also forgets the details.
So another quick question.
Yeah.
So would there be a new anomaly for baryon number under the dark U1? I mean, I didn't see the. Or is the dark sector completely vector-like?
So there is no dark U1. There's just U1 baryon number. And I'm just charging the dark sector states under that.
Okay, yeah. So there's no dark U1.
There's no dark U1. It's also, I should have been very clear about this. There's no, when I mean dark baryons, there's no confinement. There's no actual baryons. They're, fermions charged under standard model. This could, for instance, this is the same kind of models that people invoke to address the neutron lifetime puzzle, just kind of in a complementary region of parameter space.
Okay. I think we can thank Gilly again.